So the question is going to quickly become, well, how can we solve these problems without graphing? Because eventually we're going to have more than two variables, more than 2D. So let's talk about how to solve these without graphing in 2D so that whenever we go to start solving these in 3D, we'll be able to do it. So the first way that we're going to talk about solving these problems is by using substitution. So using substitution. All right. And the way that we're going to do this is essentially you're going to pick one equation and solve for either x or y. Either one works. Then you're going to use the other equation and plug in what you just got. And this might be familiar to you, it might not, and obviously this isn't the official solution language from your book. This never made sense to me. The way, anytime I solve something, I always have to come up with, this is the way that they do it, but the official words never made the same kind of sense to me as just putting it into my own words. So if my words don't make sense to you, after we do this for a while, don't just copy this down and say, oh, this is my method, have it make sense and then write your own method. As long as it follows the general path, you're going to be in good shape. Okay, so let's look at an example here. Say now we actually wanted to solve for x and y without graphing. They're not given the variables in advance. We've got 5x minus 4y equals 9 and x minus 2y equals negative 3. All right. So we want to pick one of the equations and solve for x, either x or y. Now here's the trick. You always want to go for the easiest looking one. So which one here looks the easiest to solve for? Well, hopefully you're thinking, I'm going to go for this one. I'm going to pick this one. It's basically by itself already. It's easy to get to. I'm going to put that in quotes because nothing's ever easy, but it's mostly reasonably easy to get to. Okay, so what we're going to do is we're going to take this x minus 2y equals negative 3. We're going to solve for x, so that means x is 2y minus 3. Now we're going to take, so this was the second one. Now we're going to take the one we didn't use, 5x minus 4y equals 9, and now we're going to plug in this for x. So now, instead of writing 5x, I plug in for x. What do I put in for x? Right, I'm going to put in, right, like I can tell what you said. But anyway, never mind. I'm going to plug in for x 2y minus 3. And what's happened now is you have an equation with just y's in it. So now I can go ahead and distribute the y. Minus 4y equals 9, so I get 6y minus 15 is 9, so 6y equals 24, so y equals 4. And that's part of my answer. Now that I solved for y, I can actually plug it. So we started here, we went there. Now I can actually plug this answer back in for y, because I say x equals 2y. Now instead of y, I can say 4 minus 3. So I've got x equals 8 minus 3, or x equals 5. So my answer is 5, 4. So if I want to know, where do these two lines intersect? They intersect at 5, 4. So that's kind of the nice thing, is if nothing weird happens, you have exactly one solution. So if you've got your notes over here, somewhere, there we go. So intersecting lines means exactly one solution. Another way to put this is if you're solving it by hand and nothing strange happens. You get an answer. If you get an answer, that's the answer. It's crazy, I know. Now, when you're on a test, if you're wanting to really, really make sure that you got this right, you could always take, where did I go? You could always take this 5 and 4, plug them back in, 5 times 5 minus 4 times 4, is that 9? And it is. And then 5 minus 2 times 4, is that equal to negative 3? And it is. So you can actually check your answers using the method that we did at the beginning of the section, just to make sure that you're getting your answer right. All right. So let's take a look at another example. come back. So we've got something more along this line. So we've got negative 3x plus y equals negative 2, and 15x minus 5y is equal to 10. Okay, so if we're looking at this problem, which variable do you want to pick and solve for? I'm going to go with this one, right? That one looks really easy to get to. So I'm going to say, I've got this equation, and I want to solve for y. So y is 3x minus 2. Great. Now, I'm going to take that, and I'm going to use the other equation, the 15x minus 5y equals 10. I'm going to plug it in. But now instead of subbing in for x, I'm going to sub in for y. So everywhere I see a y now, I'm going to write 3x minus 2 equals 10. So 15x minus 15x plus 10 equals 10. So, crud. What just happened? I ran out of x's, right? My x's canceled out. Okay. So when your x's cancel out, what does this mean? So let's take a look. So let's actually graph this and see what's going on. So the first one, it's 3x plus 2, 3x minus 2. And the second one, where did it go, is, that's the first one, and the second one is 15x minus 5y is 10, or negative 5y equals minus 15x plus 10, or if I divide both sides by negative 5, I've got y equals 3x minus 2. Uh-oh, so what happened? These lines, they're the same lines. So what does it mean when you have the same line? That means we have infinitely many solutions. We have infinitely many solutions. So when I look at 10 equals 10, I ask myself, is this a true statement or a false statement? It's true, right? 10 is 10. 10 is 10. It's wonderful. As long as it's true, that means that there's a bazillion different ways that I could satisfy this equation. So what I can do now is I can make a generalization that any time all my x's and y's go away and I wind up with a true statement, that means I have infinitely many solutions. So add this into here. If all your x's and y's go away and you're left with a true statement, then that means you have infinitely many solutions because you've got the same line. So let's look at one more example. Say we've got, let's look at this guy again. X plus y equals 3 and x plus y equals negative 2. Now we already know that this is no solution, so we know what to expect. And we can pick any variable that we want to solve for. It really doesn't matter because, I mean, it doesn't. You could always pick a complicated one. But we'll go ahead and pick the first one just because it seems straightforward. So I've got x plus y equals negative 2. So now everywhere I see an x, I'm going to plug in negative y plus 3. This might harken back to the composite function days. Negative y plus 3 plus y minus 2 equals 0, or equals negative 2. So my x's and y's go away, and I'm left with what? 3 equals negative 2. Is that a true statement or a false statement? False, right? This is a lie. It's a lie. So since it's a lie, how many solutions are we going to let this guy have? None, right? If you lie to me about whether or not you ate your dinner, you're not going to get any cookies. That's kind of the same way with, what you call it, systems of equations. If you're going to lie to me and tell me that 3 equals negative 2, you don't get to have any solutions. So go ahead and make sure you update your little table up here. When you have parallel lines, you have no solution. Or you could say if all your x's and y's go away and your, oops, let me move over, and you're left with a false statement, then that means that you very much have, oops, that's not what I meant, that you very much have no solution. Let me move this over here so it doesn't look so funky. I lost my S. That's okay. I'll get it. So, when you have parallel lines, that's the same thing as having something like this where you actually solve it. You get a false statement. Again, they never touch. So the statement is false. There's absolutely no solution.